Hi, my name is Cameron Olson, and I'm a student in Dr. Koda's computing class, as well as Dr. Ballerini's mechanics class. Being in both classes this semester, this was kind of a cool final project fusion between the both, and I really ended up enjoying it. And I think the synergy between the two classes was something I don't often see. Maybe going forward I will. So it was really cool. So I'm just going to go through and explain the code first, and then I'll show you how it works, give you an example or two. So it starts off with housekeeping commands: clear all, close all, a whole shebang, just to make sure we have a clean slate to work with. Then it loads the data from an Excel spreadsheet, and I'll show you what that data looks like before the test case I decided on, before we actually run the program. After that, I went ahead and set the size of the data equal to a row and column variable. That allows me to run instances of loops based on the number of rows and columns without having to repeatedly call the size and index that. Here, I initialize variables that I don't want to later in the program. I like to have it all in one section. It makes it clean and allows me to see what I'm working with and where the variables start. The first one is output, which is a matrix that will be filled inside of one of my loops. I created it outside of the loop to save time and performance. This is just going to be a ticker. It's going to keep track of how many times a loop runs. And this is going to be a while loop exit statement, but I needed it to be set to 1 for the loop to run the first time through. So here, for every row, the code checks that the value of LAB, the third value, is greater than the value of D, because that's the only way it would work physically. It wouldn't. I mean, it could work elsewise, but it wouldn't be solving the same problem. So. And if it's not, it asks the user to enter a new value for that. And it has the name of the value of the test case here, and that is just the row. Here I found LAC max and LAC min. I found the maximum by Pythagorean theorem, because right off the bat I realized that if LAB is at a 90-degree angle with the ceiling D, then it's going to be the maximum length of LAC. So I just made it a right triangle and computed it. And the minimum is the opposite. It's whenever it's 0, it's folded all the way up. So that can be obtained by subtracting LAB from D, because we already guaranteed that LAB would be smaller than D. Then I have this loop run for every instance of LAC between the min and max value, and I have it set to a fraction of the length of LAB because I assume they'll be somewhat similar. I know people could put in any sort of variables. It could be a decimal, it could be thousands of meters. I figured that would just be a good way to cover it by stepping 1/100th of whatever the length of LAB is, and it worked out well. This right here is that tracker I told you, the counter. It just increments once each time the loop runs, and that is so I can use it later to place things at particular points in the loop. Here I pass the variables D, the distance apart that they are, the weight, and the length of AB, as well as the incremented LAC, which passes through a different one each time the loop runs. And I pass those all through into my function. So that creates a matrix, and then at the outside of this loop, this for loop right here, that matrix gets put into order as the first in a 3D matrix, the first, I guess, page of a 3D matrix, and that varies. First page, second page, third page for each time the loop runs. Now there's a page matrix filled with these calculated values based on a varying independent variable, and each page is a test case instead of a row. And then lastly, it sets the instance and the output equal to 0 so the loop can rerun properly. The way I decided to plot it, I decided to ask which data set they'd like to plot, because I imagined the ability to put thousands of test cases in, and you don't want 1,000 graphs popping up or plots popping up all at once. So I allow them to view one at a time, and then it loops, and the loop breaks whenever they choose down here not to continue. And that breaks the while loop. So the first thing it does is it clears all the input. That way it doesn't pile up. Then it clears the graph, so you don't have a bunch of graphs cluttering the screen. So here I have put ease after, because these change, they're in flux. In fact, they change with each instantation of the while loop, and they just create a plot for whichever data set you choose. Based on the data set you choose, and it pulls that page of the matrices, or of the 3D matrices, and then assigns all the values of TAB to TABE, and the same for TAC and LAC. It just assigns those to row vectors, or column vectors, the corresponding column vectors, and then cuts the zeros off the back. After that's done, starts a new figure, and then I plot with all my plot commands and titling and axis setting and label setting. I plot the first tension, the second tension, and then I ask them if they'd like to see another one. If they click anything but yes, then it doesn't reset and the while loop breaks and the program's over. If they click yes, then it's gonna run again. And after this, no matter what they click, it's gonna set all the values equal to 0 to once again have a clean slate as they go through. And finally, this is my function. I use the law of cosines to figure out theta, the law of sines to figure out phi, and then I use summation of forces to figure out T1 and T2. I thought it was actually pretty simple. I was surprised. So to show you the functionality of the code, I'm first going to show you the data set that we use, so you can understand what it looks like before it gets run through the program. And here we go. We have some negative numbers right here, which will have to be changed, and a value of LAB that is greater than D. So my checks will have to go into place to solve that. So I run it. It goes straight through to test case 5 and tells me that that value is wrong. Change that to a 1. Then it asks me which data set I'd like to see. So at this point, it's run all of it. It's gotten all the 3D matrix created, and it just wants to know which one I would like to see. I'll pick 2. It's going to show me what it looks like plotted. A menu pops up and asks me if I'd like to see the other one, and I click yes. Once I click yes, it jumps to a new instance, and I enter a new one. Pops up with a new graph, deletes the old one, so on and so forth, until I click the X or no, at which case the program terminates. Some of the limitations of this code, I think, would be that, in fact, LAB could possibly be bigger than D. For example, if D was 10 and you could imagine LAB and LAC were both 20, that would be a situation that lies within the bounds of the problem, because the weight would still fall somewhere in between the two, in fact, exactly in between the 2 points A and C. But it can't account for that. This program can't account for that. And for good reason. If you didn't have those limitations, then it would be easy to put in a lot of error creating and code breaking test cases. So I think it's about as functional as it could get. And yeah, I think it's about as functional as it could get. I think it does have a few shortcomings, as well as that it can only solve, obviously, for one specific scenario, one specific setup, and that's not very ideal. But I think it would be very useful. From what I've learned in statics, this would have been very useful to, and I know they do use it. They use computer programs to test static equilibrium, to test tension in wires, to test everything. nowadays. So I think it's exceedingly useful in the field, and it makes things easier. It saves you a bunch of longhand calculations. So that is everything. That is my Project 2 code. Good luck on finals, guys.